this video, I will give a brief introduction to RTL or register transfer level design. The register transfer level of design forms the basis for digital design using hardware description languages. The primary skill that is required for a designer who uses HDL based design is to learn how to visualize a system using the RTL level of abstraction. Essentially, RTL lies somewhere between the gate level and the system level of abstraction. This slide gives you a description of the basic building block of a digital system that is represented at the RTL level of abstraction. Essentially, a system at the RTL level will consist of two broad components which are classified under the control path and the data path. The control path consists of those elements which control the flow of data in the system, and the data path will consist of those subsystems which are involved in the storage and manipulation of data in the system. So typically data path elements will be consisting of components like registers, shift registers, ALU and so forth, whereas control path elements will typically consist of state machines and the associated logic which are required for supporting these state machines. Now this slide shows an example of a serial multiplier which is represented at the RTL level of abstraction. So we know that in a serial multiplier we have registers for storing the multiplicand, and the multiplier is stored in an accumulator, and as and when the serial multiplication progresses, the multiplier bits are shifted out. So the MAC or the multiplier accumulator register is essentially a shift register. So these two registers form part of the data path, and also we have an adder as part of the data path. And here the control path is comprised of a state machine, the controller state machine, which essentially keeps track of the number of additions that are taking place during a particular multiplication operation. In this slide, we have a slightly more complex system which is expressed at the RTL level of abstraction. So here a simple processor is represented at the RTL level, and you can see that the data path in the processor consists of all the registers that make up the register file, then the muxes which are responsible for routing the data from the registers to the ALU, and also the ALU itself. So during a particular arithmetic or logical operation, the operands are selected from the register file by appropriately configuring the muxes, and the ALUs are configured by the signals from the control path. So you can see that the data path elements are configured for storage and data manipulation by signals that are emanating from the control path. And in this processor, the control path is comprised of a state machine, of course, the control unit state machine, which essentially goes through the fetch, decode and execute phases. And the state machine is supported by signals from the instruction decoder. The instruction decoder generates certain signals based on the instruction that is read from the memory. So we can see here that the control signals that are generated and passed on to the data path through the control bus lines are responsible for configuring the data path elements for performing a particular operation. So we can summarize the properties of the data path elements as primarily meant for storage or data manipulation, which essentially means performing arithmetic operations or logical operations or tasks such as shifting. Then we can also have steering logic as part of the data path, such as muxes and decoders. So in the previous example of the processor, we have seen that we need steering logic for routing data from the registers to the ALU. And the hardware characteristics of these data path elements are primarily such that they are constructed using regular structures with buses being used for communication. And since buses are being used for communication, typically these elements are characterized by large capacitances. And the critical path of these elements will significantly affect the performance of the whole system. Now coming to the control path, you can see here that unlike the data path, the values of the inputs, the logic levels of the inputs are significant. In a data path, the input values are not significant in the sense that the values of the operands will not influence the functioning of the data path elements. The storage property of a register is not altered by the type of data that is stored in the register. Or in the case of the ALU, the operation that is performed in the ALU is not affected by the type of data that is fed into the ALU. But unlike the data path elements, in control path elements, the input values matter.